Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello. In this problem, we're asked to find the magnitude of the magnetic field located at the center of a little bit of a strange geometrical combination of two loops of current carrying wire. Basically, what we have from a top-down view is two current carrying wires. So this is the top view, say from a ring of wire like this. What we're going to take is two concentric rings like this, but then put them kind of perpendicular inside of each other, like this. Basically, what's happening here, right, is two individual loops of current carrying wire. Say something like this. It doesn't matter which way the currents are going in general, so we'll just pick some. So let's say the current is heading out of the page on this side of the wire and into the page on this side of the wire. Because, right, we have some circular loop going on. If this is the case, then if using the right hand rule, if we wrap our fingers around the loop of current and try to follow that, then our thumb is going to point, in this case for this loop, to the right, and therefore we know the magnetic field created by this loop of wire is to the right. Well, this combination here on the left is just a combination of a loop like this, right? So maybe if this is the green loop, this would be the green loop here. And then we can say maybe have a red loop here that's creating a magnetic field as well. We have a red loop of wire that is heading this way. And just for example purposes, like I said, it doesn't quite matter, but let's say that the current is heading out of the page here on the left side of this loop and into the page here on the right. And if it's doing that, then that means we have a magnetic field from this loop that is heading up like this. So this problem really hinges on the idea of the superposition principle. So we have this strange combination of two loops on the left here, but really it's just the addition of the two individual situations we have on the right here, the two individual loops. And we'll see, right, if we want the net magnetic field at the center of these loops, I just have to add, we'll call this 1 and 2, I just have to add the two magnetic fields that I would get at the center of each of the individual loops together. But remember, we are adding vectors. So this vector b1 is to the right, this vector b2 is up. What matters is that they're always going to be perpendicular to each other, right? So that if we have our b1 vector here and our b2 vector here, then the net resultant one is going to be the vector addition of those two. So B net, the net magnetic field at the center, is the addition of the two individual magnetic fields. Now, if we look at the trigonometry here, that means that if we want the magnitude of the net magnetic field at the center, which would be the magnitude of the addition of these two, we just have to take b1 squared, magnitude of b1, plus the magnitude of b2, square them, add them together, and square root. That gives us our magnitude of the net magnetic field at the center. But of course, because these are the exact same type of loop, we know that these magnetic fields are going to be equal. So B1 is actually equal to B2. The magnitudes of these magnetic fields are equal to each other. So that means that the magnitude of the net magnetic field is actually the square root of 2 multiplied by B, the magnetic field created by any of these loops at the center. And we are given that equation from our textbook. We know the magnitude of the magnetic field at the center of a circular loop of any number of turns. So we're going to write that in here. The magnitude of the net magnetic field at the center is root 2 times the magnetic field at the center of a loop, which is given by the number of turns in that coil. Magnetic field at the center of a circular coil is given by the number of turns in that coil, mu naught times the current through that coil divided by twice. We'll use big R here, and that's actually for the radius of these loops. So if we know the loops look something like this, then their radii are given by this big R here. So I believe we're given everything we need to know in the problem, right? So we have root 2 here. Each of these loops is only one turn. Mu naught is 4 pi times 10 to the negative 7 Tesla meters per amp. Multiplied by the current still here in the numerator. That is given as 1.7 amps. And then we're going to all divide this by 2 times the radius of these circular loops, and that is 4 times 10 to the negative 2 meters. Put all this in our calculator, and we get that the net magnetic field at the center of this combination of circular loops is 3.8 times 10 to the negative 5 Teslas. And that's our answer.